Welcome back to our next lesson on foundation level mathematics. So, continuing with statistics, we looked last time at how to collect our data, free from bias, accurate data, and now we're going to look at how we analyze that data. We're going to be looking at things like averages, is a key part of that. So, first of all, we're going to look at the different types of average that we have, um, and what those different types are, various pros and cons of each, that sort of thing. Then we're going to look at frequency tables, which is a handy way of collecting our data together, particularly in cases when we have a lot of repeat data points, maybe because we've got a restricted number of options. And so we want to collect that together. Or sometimes maybe when there's many options and we might choose to group them together. That's an example of a group frequency table. And how can we work with these tables? And the benefits of those. So those are our different sections of this lesson. Let's start off with different types of averages first of all. So what is an average in general? So what's really useful about an average is it's essentially a single value that we can see as being representative of a central or typical value of a data set. So we've collected our data, we have a data set. We're going to be looking today mostly at quantitative data. So, because this is part of mathematics, we're interested in numbers mostly. So we looked last time at qualitative data, um, but more often than not, we're looking at quantitative data. So and that's where we can then calculate things like averages. So the benefit of an average is that it can condense even a very large data set. We can get a single data point that is like represent of that whole data set, and so it's very easy. Like say if we collected data on say different schools, for example, and you've got data on one school and another school and another school, and you don't want to necessarily compare the entire data set of those different schools. You might have a single average that's representative of those data sets of each school, and you could compare those, and it can be a lot easier to make those comparisons and then therefore make decisions um, based on those comparisons. So that's the benefits of an average. Um, Downside of it is that it's only representative. Um, it's only one value, and it doesn't take into account other nuances of the data set, like things like distribution. So you could have two very different data sets that produce the same average. And so we're not really taking into account that kind of information, although that's a bit more detailed information, which we don't really look at too much in foundation level mathematics. So you don't have to worry too much about that. But be aware of that. Some information is lost when we're just calculating an average. So and very simple tool, but if we need that additional detail, it's not enough by itself. So we're going to look at different types of average. We're going to look at mode, probably the simplest one, really. Then we've got median, and then we have mean, included what we call the weighted mean, which is something you can touch on at foundation level. Um, so we'll be considering that. So let's look at mode first of all. So mode of a data set is simply the most common value. Which one appears most frequently in the data set. This type of data average is most useful when we're dealing with, say, or perhaps qualitative data or quantitative data where we have a lot of repeat values. Maybe there's a very restricted number of options of data points that we can have, and so you're going to get a lot of repeats. And so, which one is the most common can you can be very representative of the group as a whole. Um, so the advantages of the mode, very easy to find, quite easy to understand, simply just being the most common value. Can be used for both quantitative and qualitative data, which is also very useful. Um, and it's unaffected by extreme values, which are outliers. So we need to be familiar with the concept of an outlier. So an outlier is a very extreme value, which could come from maybe it is actually a genuine data point. Sometimes it might be an error, a mistake, and so we sometimes might choose to identify an outlier and remove it from the data set. There's different ways potentially of dealing with outliers, but that's basically what outlier is. It's a very extreme value. So, say if you, I mean, from our previous lesson, we had a data set looking at the ages of people. Uh, uh, no, hold on, no, that's something we'll be looking at. Sorry, in this lesson where we've got like an example of a data set of the ages of say students in a youth group, and if you had like a data point of someone who was 5 years old or say 25 years old, those would be example of outliers. Because for a youth group, you wouldn't expect someone of those kind of ages, and that might be incorrect, or maybe it is someone who's part of that group, but they're just an outlier value. So that's what an outlier is, essentially just an extreme value. But mode is not affected by that because you're just picking the most common value. And outliers, by definition, are not going to be the most common values. I mean, if you've got many, many extreme values, then they're not really extreme anymore. That's just part of the data set, essentially. So the disadvantages is that the mode might not always exist. Maybe, so if you've got too many options of values, maybe every value only appears once. Or maybe it's not unique. Maybe you have some values that do appear multiple times, but maybe you could have two very different values even that both appear, I don't know, say 3 times. And so both of them are potentially the mode, but they could be very different values. And so which one is actually the mode of the dataset? Those kind of circumstances, the mode is not so useful anymore. And wouldn't be so representative as other averages we're going to look at. So, yeah, so this was the example I was talking about. Like, say, if you got the ages of different, uh, this could be our data set of being the ages of different students in a youth group. And yeah, so you can see now, if I had like a number 5 or number 25 or something, that would be like an example of an outlier that you might choose to just ignore. Um, but here's our data set. You might want to pause here and see if you can spot what the mode is. So it's just the most common value. Or perhaps you can see it already. The mode is going to be 14. And you can see that that's the most common one that appears here. It appears a lot. And so you see, here's an example where we've only got a very limited number of options. You basically got integer values from 13 to 17. And there's not many options there. And so you will get a lot of repeat values. And that's where the mode can be really useful to find what is representative of the group. So you see most people here are essentially like 14 years old. Let's look at median now. So median, slightly more complicated average, but a bit more useful in many circumstances. So the median is the middle of the data set. So when we're dealing with ordered data, or maybe the data isn't ordered, typically it won't be, and we'll have to order it ourselves. And then the median is the middle data point. Um, and so that's what we consider being representative of the data as a whole, where we take that middle value. So this type of average is very useful for data sets that contain outliers, because we're just looking at the middle. The outlier doesn't affect the median so much. Certainly, if it's part of a bigger data set, um, like even if you had a very extreme data point, that data point is still only one data point. So it doesn't affect the median, like the middle of the data set so much. So that's an advantage of the median, which yeah we'll see here. It's not so affected um, by extreme values, and accurately represents the midpoint of skewed data. So you don't look too much at skewed data at foundation level. So skew, just generally speaking, what skew is which way does the data set generally lean? Um, so say in that example we just had with the ages of students in a youth group, you might have most of the students, like even though we've got a range of 13 to 17, you might find most of them are 13, 14 age, and then just a few in those older ages. That'd be one that's very much skewed towards the lower ages. Or you might have another group where most of them are more like 16, 17, in which case it's more skewed the other way. That's an example of skewness, because the data might not be evenly spread over all the possible answers. Most of them might be one way or the other. That's an example of a skew. But yeah, you won't be asked too much about that really. Uh, Disadvantages of median is that it ignores most of the data points. Just focusing on essentially the middle of the data set. It's also less useful for small data sets, which can be quite unstable. Certainly, if you add like a new data point, that one data point could have a much bigger effect. Or like, so say if you had a big data set of 1,000 data points and you add one more data point, so now it's 1,001. That's not really going to affect the median much, which is just simply the middle. But say if you had a data set of only 10 and you went from 10 up to 11, that one extra data point is much more significant now, and it could affect the median. So that's an example where the median would not be so useful. So here, let's look at another example here. So say if this is a bunch of students in a group, and we're looking at their heights in centimeters, say, and this could be the heights of various students, and we want to find where the median is. So important thing, the median being the middle. Remember, first things first, we need to make sure the data is ordered, and this one is not ordered. So what we have to do, we rearrange it to make it ordered. How you might do this is you might go through each of the data points and try and number them. Um, Try and identify where the first one is, the second one, third, just going through. And if we're doing it by hand like this, the data set won't be too large. It'll be something like this, and you could try and get the correct order by numbering each of the data points we have, and then perhaps rewrite it like this, where they are then in order. That typical thing just takes a bit of practice, to just be able to get these in order accurately, where you haven't missed a data point, you haven't got one of them just the wrong way around or something. Just got to be very, very careful. And then what we can do is we can start counting in from each side. So you see we've got 135 and 180 at each end. We could then count into 161, 176, 162, 175, 163, 174, and so on. You can imagine just sort of counting with your fingers at the same time, one in each. And eventually you'll meet in the middle at 169. And now that I've circled that, perhaps you can see there are 6 data points on either side. So we can see that is the middle. And so the median of that data set would be 169. And there you go. As simple as that, just to calculate what the median is when you've got the actual data set like this. But one thing to be considerate of is so this is when you've got an odd number of data points. If you had an even number, so say here, I've got this data set now, maybe we add one more data point of someone who's 181 centimeters tall. And now it's even. If you do that same thing where you count in from each side, you might want to try this yourself now. And you'll find you'll get to a midpoint where you've got two like this, and there's no data point in between them. And so, okay, what do we now do? In this instance, what we do is we simply just take the middle of those two values. So that's not an actual data point that we have, 170, but we create, and we're not creating a new data point. We're just taking the midpoint of those two data points in the middle, and we take that as the median. So a little thing to be mindful of there, depending on whether you've got an even or an odd number of data points, you may come across this situation where you then just take the midpoint. One last thing you might want to be aware of is the range, which is not a type of average really, but it's something you might be asked about and something that's useful in certain circumstances, which is basically, well, the range of data that we have, basically the difference between the highest possible value and the lowest value we have, which in this case is 46 centimeters essentially, because these are heights of students. So you see there 181 minus the 135 and we get 46. So that would be the range. Another key word to be aware of there. Let's look at mean now, which is the type of average that we tend to use most frequently, the one you'll get asked about the most, because it does tend to be the most useful average, but typically we will calculate multiple types of average, and because each one gives us different information about the data set, so it's worth calculating. Oh, excuse me, calculating multiple multiple averages. Sorry. So here's the mean. So more specifically, because there are different types of means, we only really look at mean and weighted mean. This is when we refer to as the mean, is this type of mean, what we call it arithmetic mean, which is where you sum up all the values and you divide by the number of values there are. So this is very commonly used average, produces a typical value for the data set. And the powerful thing about this that we haven't seen with the previous two types of averages is that we're incorporating all the data sets. We're not just looking at the most common or the middle data point. We're bringing all the data points together. So it works best when we don't have too many outliers. The advantages of the mean, is that it uses all the values, so it'll be more representative of the data set as a whole. and it's still relatively easy to calculate. There's not too much more complexity to it. The disadvantage is that because it uses all values, this includes the outliers. So sometimes we would want to be more careful with if we have outliers and should we include them or should we not include them. Sometimes we'd eliminate that from the data first and uh, before calculating the mean. It depends. So that's something we need to be aware of. It's also not going to represent skewed data so very well. So if the data is very much skewed in one direction or another, that's going to definitely affect the mean. The mean will shift with that skew. So which is something you may want, may not want. But yeah, I don't want to go too much into that. So here's an example. If we've got, say if this was someone's small business and this is the amount of money they made in each month. So you see they've split up into quarters. You've got your January, February, March. Then you've got your April, May, June, and so on and so forth. How much money we made in each month. And we want to calculate the average, well, the mean. So when you might have a question that asks you to calculate the average, the word average, even though that as we've seen, there's technically different types of average. The word average is sometimes used synonymously with mean. So if you get a question that asks you to calculate the average of this data set, typically that's what it's referring to is this mean. So how do we do that? What we need to do is add up all the data first. And so if we add up all these amounts that we earn each month, you get to the total amount for the year, which is a useful data point, useful piece of information itself. And then we divide this by the total number of data points, which is 12, 12 months in a year, and we get this value, 3,550. So that's the amount of money that we made each month on average. So you can think about what we've done there. It's like we've collected together all the money, and then it's like you're now spreading it evenly amongst the 12 months. And that even spread produces 3,550 per month. So there's an example of the mean. So I just want to look at weighted mean quickly, just in case you do come across this. Very similar to regular mean. So where each data point is weighted. So a weighted mean is great when you're trying to calculate the mean of a data set, but where the data has different relative importances or otherwise they just contribute to the total differently. So the advantage is that it can take into account this relative importance of each data point that have varying contributions. But the disadvantages is say if the situation is such that the weights that you apply to each one is not so obvious. If you don't get those weights correctly, I mean that could drastically affect this mean that you're going to end up getting. So you'd have to make sure those are assigned correctly. But you only really encounter something like this, like a simple example of say if you're looking at your scores to in a particular subject, say math, and you have a test and you get a score of 80 out of 100, and the midterm you get a score of 56, and then maybe there's a series of coursework you do as well, and each there's 4 of them you did, and these are the scores you got on each. But so now when we're trying to calculate your overall score, which is going to be the average of these, it's not going to like add them all up and divide by 6 because there's 6 numbers. This is going to be weighted based on the relative importances of the different scores. Like the test and the midterm are going to be more important than the courseworks. And perhaps the test is worth 50%, the midterm's only worth 30%, the courseworks are worth 5% each. How would we calculate the weighted average here? What we do is we take the weighting of each value. So we do 50% of the 80, which is 40. We do 30% of the 56, which is the 16.8. And we take 5% of each of these values for the courseworks. And then we just add them all up, and that will get us our weighted average of 71.4. So we don't have to then take that 71.4 and divide by 6 or anything like that. We just add them up because we've already essentially accounted for that here. Like if we think back to the example we just had a moment ago, where we was looking at the average amount of money earned over a year. So we added them all up and we divided by 12. But another way you could think of it is basically multiplying each one by 1/12 and then adding them up. that would essentially have the same result, wouldn't it? And so it's basically like the same thing that we've done here, except the weighting would be the same. You times each one by a 12th. Here, we're doing, that exact same thing, but the weighting is different. So we're not timesing each one by a 12th. We're timesing, well, the first one by a half, the second one by, 3/10, the remaining one by 1/20th for the courseworks. So you can see it kind of works very similarly, but here just the weighting's different. So that's it. That's different types of averages to account for. Um, what are the advantages and disadvantages of each? Let's now move on to how we collect data. Well, not how we collect data as in like what we did last time, but once we've got our data, how do we put it into, say, like a table? An example here, frequency table, which is useful under certain circumstances. So say here, a frequency table is a way of collecting data that works well when we have a limited number of values. So we're going to get a lot of repeat values. It will consist of two columns at minimum, sometimes more. And the categories of data we're collecting, and then the frequency of data in each category. So here's an example of, say, like this could be data collected by an estate agent about different properties in their local area. And you might have the number of bedrooms, which goes, say, from 0 to 5. 0 being like a studio apartment where your bed might be in the living room or something, and so there's not technically a bedroom. So that's like a property with no bedrooms. And then the frequency of properties that we have corresponding to those number of bedrooms. So you got small flats that might have one or two. Then you have houses that might have 3, 4, 5 bedrooms. And we can see how many belong to each category. So if we wanted to calculate averages from this data, you need to kind of be able to see the original data set here. So based on this frequency table, we can actually recover the original data set if we wanted to. And then we can just apply the averages and that we've seen so far. So this data set would essentially look like this, where you see we've got we've got 7 zeros. We then have 46 ones. We've then got 29 twos, and so on and so forth. 11 threes, 6 fours, and then 1 5 at the end. So this is what the data set would look like. And so, okay, you can see this is not very practical, even if you just generally have a large data set. But certainly once you've got a data set like this with a lot of repeat values, this is not the best way to represent it. So this is an example of why we've used a frequency table here, because you see it's a lot neater and condensed. But kind of in your mind, you've got to be able to see the original data set. Kind of what this frequency table represents essentially, and this is what it represents. So if we wanted to now calculate some statistics, some averages or whatever from this, with this understanding, we can now do that. So you got obvious things like minimum value we can find quite easily, maximum value being 5. So we could then also calculate things like the range if we wanted to, no problem there. Say if we wanted to calculate the median, how would we calculate the median? Well, the median here is going to be 1. And how we would go about doing this, we don't really want to do it like the way we've just seen before, which is handy if you've got a small amount of data where you start counting from one end to the next and see if you get into the middle. You see here when we've actually got 100 data points, that's going to take ages. Instead, we think more generally like what a median is. Remember, it's the middle data point. So you see here, we have 100 data points, which you can find out by adding up all those frequencies. You'll see that means we have 100 properties here. And we know the median is the middle point, so it's basically going to be the 50th data point. So what we can do is start, like this frequency table it is kind of already ordered, isn't it? Like you see you've got 7 zeros, and then 46 ones, and then 29 twos. In that table, it's already essentially ordered. And so if we wanted to find the 50th data point, we can determine where that's going to be by working our way through this frequency table. So we look, okay, is it going to be 0? No, because you see the frequency of 0 is 7. So that means the first to the 7th data point are zeros. We want the 50th data point. So, okay, so it's not in that range. So we look in the next one, the 1, which is 46 data points. but that's after the first seven. So it's if we do 7 plus 46, that's going to be 53. So from the 8th to the 53rd data point are going to be ones. So the 50th data point, you can see that lies within that range. Between the 8th to the 53rd, the 50th data point is just about within that range. And so that's how we deduce there that the median here is going to be 1 because it lies in that range. The mean, how would we calculate the mean? Again, we don't want to go through adding up all these values, 1 plus 1 plus 1 plus 1 plus 2 plus 2 plus 3. That'll take forever. Using the frequency table, we can almost, so we need the sum of all the data first, and then we divide by how many data points there are, don't we? That's basically what the mean is. So we could calculate that sum like this, because we know we've got 7 zeros, we've got 46 ones, we've got 29 twos. So if we, multiply each of these, types of data point, 0 to 5, by their respective frequencies, that's then going to give us the total of the data set, which is, we can work out each one individually, and then you see it comes to 166. So what this represents is how many bedrooms are there in total across all the different properties. And so now if we want to find the mean, we do that 166 divided by the total number of properties there are, which is 100, and that will give us the average number of properties, the average number of bedrooms, sorry, per property. And you find that comes to 1.66. And that's an important thing to take note of here, is that the average doesn't necessarily have to be, like say here, the number of bedrooms is discrete, isn't it? And it's there's certain integer values it takes, but the mean doesn't have to necessarily be an integer value, because it's not an actual data point. It's a value that is representative of the group as a whole. So when we say the mean is 1.66, we're saying that on average these properties have 1 to 2 bedrooms, sort of closer to 2 really than 1. That's essentially what that means. So we don't have to round to the nearest whole number, unless of course the question that you're posed asks for that, in which case, yeah, of course, round. So that's an example of dealing with frequency tables. So let's look at grouped frequency tables now, finally, which is the same concept but just extended a little bit. And there's a couple of challenges that come with this that we need to be aware of. So let's look at something like this, where, say, a company has tracked the amount of time people spend on its website. And we've got various groups. So this is an example of continuous data, like time. It's not specific date, points. Someone could spend any amount of time, say here, between 0 and 30 minutes. And what we've done is we've put them together into groups. So we've got the first category, which is people who spend 0 to 2 minutes on time on the site. So T is the time that people spend. And the first category, yeah, is the ones that spend 0 to 2. The next category are those that spend 2 to 4 minutes. The next category is those who spend 4 to 6 minutes, and so on and so forth. And notice that not all the categories are very equal size as well. Like the first ones are only 2 minutes in width. The later ones are, 6 or even 15 minutes in width. Also notice that the inequality signs, we've made sure that the categories don't overlap. So it's the similar idea that we saw right back when looking at questionnaires. So say if we had someone who spent exactly 4 minutes on the site, we know precisely which category that's going to go in. It's going to go in the second category, not the third, because the second category is up to and including 4 minutes. The next category is strictly greater than 4 minutes. So we haven't got that overlap there, which is important to be for group tables like this. And so just like the other frequency table, we then have the number of people that fall into each of those categories, those groups. And clearly this website gets a lot of traffic. There's lots of people going to this website, and we can see here how many fall into each group. First of all, if we wanted to find the total frequency, we can do that the same way as before. But just adding up all those numbers, and you see we get quite a big number here, 32,696 over this time period. That's number of people that visit this website. Where it comes a bit trickier is, say if we was trying to calculate something like the median. We couldn't get an exact value in this case, but we could find the category that it belongs to. So if there's like 32,696 people in total, if we half that, that means it's the 16,348 value is going to be where the median is. It's a bit tricky here because we've got some bigger numbers, but we can deduce that so that the first category is going to be is the first to the 6,248th person. So we're applying the same logic we did before. So that's the first 6,000 or so belongs to that first category. The next category is then the next 7,000 odd people. So we see, specifically, it's the 6,249 to the 13,504. Usually, you're not going to have to be that specific unless, someone is right on the boundary between one category or another. But if you've got big numbers like this, typically that won't be the case because that'd just be a bit nasty question, really, to do that. So you see, okay, so it's not going to be in the first category, it's not going to be in the second category, but you see that third category goes from that the sort of 13,500th person to the 20,500th person. Well, that is the category that our 16,348 person is going to fit in, isn't it? And so therefore we can deduce that the median, see my head's in the way there, let's put you up there. The median is going to belong to that category. So we can determine, we can't get a specific value, but we can get a category. There is a way we can estimate the specific value, but that involves things like quartiles and cumulative frequencies, which are part of only the higher syllabus. So in foundation, you don't have to worry about any of that. But we might have to find, say, median to the nearest category like this. And this is a more advanced example. We've got bigger numbers, but you see the same logic applies in how we would find the median, that middle value. So let's move forward. So we've got the frequency there. So we still want the total frequency because we're going to need that now, where we're going to try and calculate the mean. Now, calculating the mean here is going to be a bit tricky because we don't have the exact data points. Like, say that first category, we've got 6,248 people belong in the category of 0 to 2, but we don't know where in that category those people are. And so we don't know the actual data points, and so we can't add them all up in order to find the mean. So what do we do here? Well, what we do is we estimate. And okay, how can we get the best estimate possible? Well, let's first of all consider that first category. So say if we've got that category of 0 to 2, and imagine that like a line here, 0 to 2. Let's say if we just assume everyone is at the value of 2. That wouldn't be the best thing to do because for all we know, that all the data points could be nearer the lower end of 0, in which case we're going to be far off. We could be potentially as far as 2 minutes off of the correct value for some of those data points. So we wouldn't want to go at that end. Nor would we want to go at the other end of 0 because we get the same problem. All the data points could potentially be closer up this end. In which case, again, we could be as much, if we assume they're all at 0, we could be as much as 2 minutes off for each data point. So what we do is we take the middle point, 1, in this case. So, because you think about there, whether all the data points are at one side or the other side, or maybe they're evenly distributed amongst the across the interval, which, is normally what will be the case in most cases. So you see there, you can only ever be off as much as 1 minute in this case, as opposed to being as much as 2 minutes, which is great. We're kind of minimizing the maximum possible error we could make. Plus, like I said, a lot of the time, data will be evenly distributed across the interval. In which case, some of them are going to be overestimating, some are going to be underestimating, and those positive and negative errors will kind of cancel each other out a lot. And so that's how we get the most accurate possible estimation. So some of these concepts of estimation that we looked all the way back in the first section of this course, looking at numbers and stuff, you might want to recap that lesson on estimation techniques if this is a bit confusing to you. But yeah, that's what we're doing here. So we can only estimate the mean, but we're trying to do it in such a way where we minimize the potential error we're going to get. And so this is what we want to do. We basically take the midpoint of each category. So 0 to 2, the midpoint's 1. 2 to 4, the midpoint is 3. 4 to 6, the midpoint's 5, and so on and so forth. You say between 6 and 9, the midpoint is 7.5. You can always find the midpoint by essentially taking the average of the two values either side. So if you do 6 plus 9, which is 15, divided by 2, gets you your 7.5, and so on. So that's how you can find the midpoint quite nicely. Certainly, if you had two decimal values either side, it might be more complicated. So yeah, just add them up and divide by 2. That'll get you the midpoint. And then what we do is we calculate the average in the same way we did before, assuming that every data point in these intervals are at that midpoint. And so this, say first of all, we want the sum. So what we do 6,248 lots of 1. We do 7,256 lots of 3. We do 7,102 lots of 5, and so on and so forth. We add all that up, and you see I've done that little squiggly equal sign. That means approximately equal to. And then that sum comes to this value. So yeah, it's approximately equal to this value because we're estimating here. So it's probably not going to be that exact value, but that's our best estimate. So that's the total, the sum. Now we can do that average by taking that sum and dividing by the total frequency, which we know what that is by adding up all the frequencies. We already found that was 32,696. So a little bit of a typo in that calculation there. You see, I put 32,996, supposed to be 696. So yeah, that is my error there. So you calculate the value, and it comes up to approximately 6 minutes, just over 6 minutes. So that would then be our best estimate of the average. Around about 6 minutes is what people are spending on this website. So you see with grouped frequency tables, even though there's times where that's useful to do that, to collect things into groups. But it does make things a bit complicated when calculating averages. And sometimes all we can do is get an estimate like this. So that's the challenge of group frequency tables. But that's it. That's as much as we need to know really about group frequency tables at foundation level. So let me leave you with this interesting fact about statistics. Something we need to be very wary of with statistics is correlation and causation. So sometimes we'll see correlations between different things when there's not necessarily a causal link. And this is an error in statistics that people sometimes fall into, where you think there's a causal link between two things when actually they're just correlated. And like a prime example would be, say, a business that might be, tracking the sales they make of sunscreen and ice cream sales. And you see they both tend to go up together and they both go down together. And you might think there's a causal link between the two. Maybe you think, oh, okay, buying ice cream makes people buy more sunscreen or something. It might sound a bit silly, but this is an error that can happen sometimes. When no, there's not actually a causal link. There might be a third thing, in this case, maybe being hot weather. Hot weather, which then causes people to buy more sunscreen, but it also causes people to buy more ice cream. And so there you go. You see, there's these two things that are correlated, but there's not, one doesn't cause the other. And so I wanted to leave you some funny examples here. Like you can sometimes see weird correlations between things that don't actually have any causal link. So here's an example, like between say divorce rates and the consumption of margarine. Like there seems to be this correlation, but they're probably not causing one another. Or here, like so this is real data, by the way. Like the consumption of cheese and then the total revenues made by golf courses. And you see again, they look correlated, but they're actually, they're almost certainly not the causal link. Here's one last example between like the arrest of juveniles and the honey produced by bee colonies, and there seems to be like an inverse correlation. As one goes up, the other one goes down. And again, this is probably just a strange correlation that has occurred, but there's no actual causal factor. So yeah, again, this is something the statistics is a really powerful tool, but it's so easy to make false conclusions. So this is something we have to always be wary of, like biases. Um, it can lead us to false conclusions. So here you go. Here's the summary of our lesson today, and then next time we're gonna be looking at our last lesson on statistics, which is how do we represent the data. So we've collected our data, we've analyzed the data, Now we're going to look at how do we represent it in graphs and charts and things like that, which are really useful to be able to, it like a graph with an equation. It allows us to see the big picture. We're going to see how we can do that with our statistics. So I'll see you there for that lesson.